All right, so what we're going to look at in this part is trying to figure out what angle something would have to be sent to go a certain distance. And so let's take a look at this here. Let's say that we had, maybe our same example we used before, a human cannonball. Someone's going to be launched through the air, right? So let's say that we know what v initial is going to be. We know how the launch velocity is going to be. We know how far the net is, right? And so we have the net set there. The question is, what angle, theta, do we want to send the person? And we can do that based on using the equations that we know for motion. And so as we get started here, you can work this out with me as you can write this out and then pause as you need to. We know that time in the air is based on our y motion, right? And so, in terms of delta y, right? Y final, y initial, y final and y initial are both going to be 0 here. So the change in y is going to be 0. And so we know that. And we know that the launch is going to be at an angle. We have certain velocity at an angle. We have Vx, we have Vy. And what we're going to do is going to replace this in terms of trig. So cosine equals adjacent over hypotenuse. So the hypotenuse is Vi. So cosine times velocity initial is going to be Vxi, what the initial x velocity is going to be, and that's going to stay the same the whole way. Now for the y, we're going to have sine equals opposite over hypotenuse. The hypotenuse again is Vi, and we have the angle. So in terms of the trig, what Vy initial is this, and what Vx initial is this, right? Just putting in terms of the trig and the in terms of the trig and the initial velocity. Okay, so once we've established that, we can place this into V initial here, Vy initial, and to have this in terms of a trig function. We can simplify there and factor t out, and we can do that. Next, we can bring v sine theta over to the other side, and we have negative v sine theta, and then our acceleration is going to be negative 9.8. So our two negatives will cancel out, and what we can do is multiply both sides by 2, and to get rid of the 1/2 on that one side, and then divide both sides by acceleration here to get time on its own. So now we have something in terms of time. This is what the time will be in the air dependent upon what the angle is, what acceleration due to gravity is if we do this on Earth, and then the initial launch velocity. So we're just putting in terms of one variable there in terms of the initial. Now for the x, we know it's Vx times time, and that's going to be, for a projectile, it's going to stay the same x velocity all the way across, same x velocity. So we can place in for Vx, Vi times cosine theta, and that's helpful because we can leave everything in terms of Vi, and so we'll place, in for time to Vi sine theta, and there we go. This is our range equation, how far an object will go. Now, we have cosine theta and we have sine theta, and so we can simplify that. We'll just bring 2 to outside to the front, and Vi is squared. We have 2 of the Vi's, and then cosine theta times sine theta. So if we have 2 cosine sine theta, what we can do is this identity, we can bring this together for sine of 2 theta and bring it all together. So we have V initial squared times sine 2 theta over acceleration. And this will give us, if we can solve for, if we want to, we can solve for what angle that we need to go. If we know the angle, we can solve, for how far it's going to go if we know the initial velocity, and so on. So what we're going to do now is if a ball is going 54 meters and it was hit at 40 degrees, what velocity should it be hit at to be able to do that? And so now in class I have you guys practice the derivation and then solve this, and so it would be good to to practice the derivation and then and solve. And so just if you are watching this on Make, I've just followed the instructions online, but yeah, go ahead and calculate this out, and then hit pause, or hit pause now. Go ahead and calculate this out and figure out what initial velocity it would take to do that. And then when you're ready to check, you can hit play to continue. Okay, so we'll place our values in there. Now, the 2 times the 40 have to be inside, and so you actually take the sine of 80 there, and you'll end up getting a velocity of 23.18 meters per second, and so that's the launch velocity to be able to go that 54 meters. Yeah, and so this next part, according to this equation, what is the best angle for maximum horizontal displacement? What will maximize the horizontal displacement? Well, if you think about it, right, what's going to make this number the biggest? If you can get sine of theta to be, if you can get sine of 90, right, sine of 90 is 1. And so, yeah, so that could be perfect, right? You'd have v initial squared times 1 over acceleration. Anything less than that is going to be a fraction, and it's going to make the range go smaller. So that's where 45 degrees is the best angle to be able to get the largest displacement. And that's a really critical thing.